So if it's log xm, then you will type log 4.0 is -6. Okay, so this is the issue of log lah, what to type. So if it's like this, you type that lor, and then you get -5.39. Okay, second thing, SF, right? So when you have, you see this one is 2SF. So when you reach here, it should be 2 or 3 dp. Log is the one that is reversed. SF become dp. Everything else is SF to SF. Okay, but calculation for log is a bit special. So let's say I take 3 decimal point. So that will be 5.398. I can also take 2 decimal point, but let's say I take 3. So this is -5.398. Okay, but sometimes they could ask log x / 10 to the power -6m. Then this one, the way you press your calculator is you don't include the -6 because the -6 is, you are assuming that you are taking log x where x is already 10 to the -6. So this one, you are actually taking log 4. Log 4.0. Log 4 lah, okay. 0.6020. 3 dp, 0.602. Very different, Means would they give me another prefix? If they are doing that, they are being quite evil, but I think this is the actual trend. Okay, second thing. Is there a unit for these two? No, the unit is inside the log. When will the unit appear again? When you anti-log them. Okay, so think about the log process. Let's say now you want to convert this and get back your x again. The value of your x again. So what you will do is, now you will say x is equal to 10 to the power of -5.398. But the unit for x is meter. Okay, so this unit transfer to here. So let's say I press my calculator again. 10 to the power of -5.398. Ta-da! 3 point, okay, not close enough. I will get meter, in meter, 4.0 times 10 power -6, and my calculator crash. 0 times 10 power -6 meter. Okay, so if I do it for here, then my unit will be -6m. So when I transfer out, when I anti-log, when I unfreeze the log, when I bring apart the log, I don't know what's the correct word to say this, but whatever you get here, when you press anti-log, this will be times 10 to the power -6 meter. Okay, so when dealing with prefixes that is inside the log, you will only unfreeze the prefix when you anti-log this. So it's probably only after you find the gradient and the y-intercept and they ask you to use the equation to find other values. Maybe part E or part F. Okay, anyway, the calculator crashed. So if you press this one is 10 to the power of 0.602. Ta-da! So it's still 3.999, which is 4.0. Okay. Can chat okay or not? Is this okay? So hopefully you get the idea. Prefix and units will unfreeze itself after you bring the log over. If you have it inside the bracket of the log, then you log based on whatever unit it is. So if let's say it's /meter, then you should type log 4.0 times 10 power -6. If it's /10 to the -6 meter, then you should just only type log 4.0. Another hint that you mess up there is, think about the axis. If let's say this is your y-axis, let's say you type this one, okay, and then you open your y-axis, it goes like 0.2, 0.4, 0.6, 0. Whatever, and you totally don't even have negative. That means you press wrongly liao. Go back and read again. Don't panic, okay? Because the good thing about, or the not good thing about paper 5 is that they always give you, oh, this is a log 1. Yes, very nice. They always give you axis bar. Load. There we go. So if let's say you cannot plot your graph, means something is wrong. Okay? You get my point? So yeah, that would be a good indication that you're on the right track, especially when it comes to log and lon. and don't confuse. So I think generally you will only get confused when you go back lah. Take the second step. Okay, so today and people who are here, we are going to mark some people's paper, okay, to try to learn from their mistakes. If you have papers you want me to look at that is different variant, if we have time, I will do so. If not, then we watch and learn lah. Okay, so this is the paper from May, June 20, paper 52. Let me pull it up first because we need to stare at the question. We need to stare at the question. Need to be inspired by the question. Sorry, too much exam prep now. My brain is a bit fried. Okay, so this is the question. I think I'm gonna crop the question so I can draw on it. So this one, and I will hide the author so I got more space. I'm gonna park this here. And I will teach you how to mark your own work lah when I'm not available to mark for you. So the ability for you to evaluate your own procedure is probably as important as writing the procedure itself. Because when you go to university, if you make a mistake in the lab, you wait for a lecturer to correct you. It might be 2 weeks later, okay? So if you learn how to troubleshoot your own stuff, that would be great. Okay, let's read the question first. Let me zoom in. So in this question, a student investigates stationary waves with an elastic cord of circular cross-section attached to the load. Okay, so there's a vibrator with a very strange position. Shouldn't a vibrator be here? Okay, I shall not ask questions. Okay, there's a cord. So I guess the vibrator will vibrate the string and then the load will adjust the tension in the string. Okay, the frequency of the vibrator is F. So whenever you approach a question one, harvest all the alphabet. You know, like you play Minecraft. First thing you do, when you respawn, is to harvest all your, I have no idea what happened there. Harvest all the wood lah, same idea lah, okay? So you harvest all the letters. This L, immediately you should think measure using meter rule. Okay? And the frequency vibrator of the vibrator is F. So this one probably need to connect to something that will cause it to vibrate. So this one is normally connected to a signal generator. A signal generator is just a device. Wait, this just for the people, because you see in a normal day, normal time, you will be able to see lah what a signal generator is. You can even find it in a normal high school lab. But unfortunately, things are not common these days. So then Google is your best friend. Okay. So a signal, the old one, okay, the new signal generator look like this. Okay. So we can plug this to the motor of the vibrator, the output. Okay. So then it will create some form of vibration along the any kind of vibrator. Okay. So it's just a box that you can turn a knob to adjust the frequency. And then you can plug your device in and that device will vibrate according to said frequency. So there's a motor inside the vibrator. When you connect to the signal generator, it will vibrate the motor. It's a little bit like, you know, your massage chair. Inside a massage chair, there's a signal generator that creates alternating current signal. And that will create your motor will vibrate. No? I don't know whether massage chair is still a thing. During my time, it was a big thing. Okay, anyway, a student investigate, oh, this is important, how F varies with cross-sectional area A of the chord. So among all the alphabets that you can, all the alphabets or the physical quantity that you can determine, right, you will notice that they will always tell you to find or to test the relationship between F and A. So if you're testing the relationship between F and A, it means that one of these is your dependent variable and one of it is your independent variable. my method is I build table because you know I am quite a scatterbrain. I don't know about you. So I build a table of constants. Okay. Today, do I build it differently? Sure. I'll build it differently today. So my first constant is F. Frequency of the vibrator. The second constant is A. I don't know because I can control both of these actually. Frequency can be controlled using a signal generator. Cross-sectional area of the chord can be controlled by using chords of different thickness, I think. Okay, hang on, let me close all my other stuff because if not, later all sorts of things will crash. Right? And let me check the chat. Okay, I will address the chat after I finish discussing this question. Okay, so I think it's easier for you to control your A because how will you know that standing stationary wave is formed? Because you are, after all, investigating stationary waves. So you imagine you do this experiment. What we will probably do is we will change different chord. You know, like your guitar, if you play guitar or bass or any string instrument, the thickness of the string, which is the cross-sectional area of the string, will determine the pitch of the note, right? So that pitch can be found by changing the frequency until you get maximum amplitude. Maximum amplitude. So how does that maximum amplitude look like? Let me find a nice GIF for you. And give it some minutes to load. You've probably seen this before. Okay, so I'm going to start listing down. I think I can change my A. So what kind of variable is this? Of course, we also have the other things such as L. And what else do we have? Equation is the best place to harvest. They're all here. Unless you don't know what the term is. There's L, there's A, there's F, there is M. What is M? M is the mass of the load. Okay, M. Then. And this question is asking us to find the value of K. Okay, I'm going to put K here. So this will be the dependent variable. This is the independent variable. All this is constant. And no, K cannot be constant because K is already told to be constant. There. K is a constant, so that one no need to write. All right. So how to measure? Instrument plus setup or method. Okay. So how do you measure the frequency? Is you adjust the vibration of the vibrator. So let me show you this. In this case, the tension of the string is fixed. So what I'll do is I will adjust the vibrator. If you can look at this, I'll adjust the vibrator until I see standing wave. Okay, until standing wave is observed. So 15 hertz, okay. 30 hertz, okay. 45 hertz, okay. 51 hertz, there's no standing wave. So when you get a standing wave pattern, what you will get is something like this. And normally we let students do this experiment at the end of SEM 1. But you know what happened at the end of your SEM 1? Yeah. So this is the pattern that you expect to see. Or something like this. Actually, it's close to this because we give you white color string. So it's pretty obvious one. It will look something like this. So if it's neither here nor there, like 51, slow motion will get something like this. Basically, it will look very messy. Okay, and your vibrator actually looks like this one. So what we are doing is we have a vibrator here, and then this side we hang a load. So you can see this part, actually, I'm pretty sure that this string actually is tied to a load because I need to adjust the tension of the string such that we get a nice pattern now. Because sometimes if the tension is too big or too small, you cannot observe the wavelength or the complete wavelength stationary waveform here as well. All right, so this is actually the whole setup itself already. Wow, can be inspired, but yes, you can follow, you can copy that one later. So this dependent, the way to do it is we will adjust the signal generator. So it's just a box that creates changing output, okay, changing output so that you can connect it to a vibrator and the vibrator will vibrate. Okay, so adjust signal generator until standing wave pattern. So basically imagine you're doing this in the exam until this one is observed. Whether you write this like that or not, up to you. Cross-sectional area is the independent variable. So how do we measure cross-sectional area? We use, let's say the chord is a normal chord. Like think about your guitar string. So we definitely need a micrometer for this, right? So we'll use a micrometer and then we measure diameter. Hold on a second. If measure diameter, circle shape must measure several position, correct? So if you can, you add here, measure at several position and average. Okay, wait. Means we measure diameter, we need to find area. So got important equation should include A is pi d square over 4. Okay. If we want to keep L constant, so we should measure this using a meter rule. Think maybe need to clamp as well because you're going to put a meter rule behind this. With your hand, you hold, cannot lah, okay, you clamp it at the back, okay. This mass, do we need to measure mass? Miss, okay, to answer your question, it's time to do the second big portion of the setup or what is required of you in this paper, which is to linearize the equation. Hopefully, this is relatively painless for you, but we can do slowly. I square both sides because I don't like square root. If you like square root, you can keep the square root. Why I put m square here? I square both sides, so this is 4l square. F square is 4l square. M over Ka. All right. So if I think about it, I can just have m over 4l square K times 1 over A. I take out the A, and I compare with the general equation of my beautiful Y-intercept. Okay, so if I compare this with Y-intercept, this one is Y is equal to mx. This one is x. And the other one in the bracket is m, your gradient. Okay, so hence, gradient is equal to m over 2l square K. I think you can keep it this way lah. Okay, no, I mean keep gradient in this wording. If you use m for gradient and m for mass, it's going to be a confusion. So if you really want to use the alphabet, you can use capital G. Okay, if you want to. I'm not going to do so. So what I'll do is I'll just exchange place. K, I'll do a swap. Swappity swap. So K will be 2l square times gradient. And I must include this here. All this you write later, maybe got marked lah. I show you lah later. Okay, must include this here. So this M must measure. How do we measure mass? Top pan balance. If you don't know M, you can't find K. You don't know L, you can't find K. And if you don't know what L is, how can you be sure it's constant? Maybe halfway in the experiment, the loop on the vibrator moved. You don't know, right? So once you have this table, it is easy for you to write your experiment. So this is the thought process. Every one of these have marked. You may have worries about what if there are certain things that they tell me to measure or I need to measure, but I don't have the actual, I don't know how to measure it lah. That one is a bit of, I want to say lack of practice, but then I can't really blame because it's COVID-19. But it's okay. I have a handy dandy list that I don't know whether you have seen it before. If you have not, well, you got time. Okay, so this is my list. Every possible thing that I can think of that they will ask you to measure. is all included here, and whatever additional detail that you can commonly write, I have also included here. If got, you add law, okay? And if let's say you want to see an example of the experiment, like for example, this one, MJ20 paper 52, the paper that we are doing right now. Then repeat different precision average, okay? Can. Okay, that's all I want to say. You can use that if you know where to have a hard copy, those of you who are here now. Okay, we can start now. Let's go mark paper. Ding, ding, ding. Okay. So normally, my coaching towards students is to write in point form like this, because it's easy to mark. Independent variable is the cross-sectional area, frequency of the vibrator. So here is already P1. Okay. This will already be enough to give you a P1 mark. Okay. Keep the mass of the load constant. This is P1. Okay. So now the statement of problem 2 out of 2, the candidate can identify what are the variables. Step 1, can you identify the variables? Step 2, can you reasonably measure everything? Not with detail. Let's say we don't talk about detail first. Do you know how to measure frequency? Do you know how to find area? Do you know how to measure length and mass? Basic first, okay? So all the first few marks are basic marks. So using an electronic balance, measure the mass of load M. Okay, this one is actually additional detail. So I'm going to change color a bit. This is an additional detail mark. Okay, using meter rule, clamp horizontally, measure the distance between the point of the cord and between the center of the pulley. Record the distance as L. Very nice. So if you measure L using the meter rule, they interestingly didn't include. Very nice. They did not include the measurement for L. That's just sad, but you can write. Okay. So 2 meter rules of same length are clamped. Oh, so that you can read both sides and then average. 2 meter rules of the same length are clamped vertically at each point. The meter rule is clamped horizontally to oh, so you're putting 2 horizontal meter rule here as reference. Okay, I see what you did there. Normally, if this is an important measurement, this is a good step, but maybe this is not as important. See, what is the main character here? F and A. So that is where most of the M marks are. All right, next point. Using micrometer screw gauge, measure the diameter of the cord. Okay, so using micrometer screw gauge to measure diameter of the cord, this is the first method mark. Okay, M1. And then take reading at several different points and then average. So taking readings at several different points, this part here is D1 and take average. Okay. Area is calculated using pi d square over 2. Okay, so this is another extra detail mark. So this is what I mean by the main character is area. Sure got mark 1. Connect the load to the cord, turn on the vibrator and adjust the vibration until the first harmonic pattern is seen. Okay, let's see. Turn on the vibrator and adjust the vibration. How do we adjust the vibration? Signal generator. Okay. Using CRO to measure T. So is your vibrator connected to a CRO? Oh yes, it is. Okay lah. Can. So you can use this to calculate the frequency of the vibrator. Okay, so if I see this is your D1 mark. Okay, and then you measure the period on the time base. But you did not mention how. How to measure T on CRO. Normally, you assume you are writing a recipe, your lab experiment instruction is for the most blur person who must be even the person who never stepped in the physics lab before should know what to do. So how do you measure T on a CRO? So what can be written is you take time base multiply by the length of one complete wave. Okay, repeat the chord using different cross-sectional area, use same type of material, use same mass, do not change position of the pulley. So the fact that you say L constant on top, I remember, and this one L constant, this is another D1 mark. Okay, repeat steps 4 to 7 to obtain average value of X. What would be better here if you were to say repeat steps 4 to 7 for the same chord or the same A and obtain average values of F. Use chord of the same material. This one is another D mark. Okay. But then when you use CRO to determine frequency, this one is already 1D. Time base times length is another D. Wow, many marks, huh? You measure area related measurement correctly is 3 marks. Frequency related measurement correctly is 3 marks. You didn't connect to signal generator, so there's one M1 loss. Stationary wave pattern is observed. So this part where you say you turn on the vibrator and adjust the vibration until first harmonic pattern is seen, close enough. So this one would be M1 mark. Okay, time for analysis. So for analysis, first thing first, I look at a sentence like plot a graph of something against something. FO10A is okay. So this is our A1 mark. Okay. Gradient K is M over 4L square times gradient square. Okay, correct. A1 mark because he used a different axis. Okay. This alone is not enough. Okay. Write out this sentence. Very important. Again, because they are looking for this sentence. So a reminder again must be K equal to something, something, something. You write, if you stop here, there is no mark. If you stop here. Okay. Last one, relationship is valid if it's a straight line passing through the origin. Very good. There's no Y-intercept. A1. Safety precaution. Place sand tray below the load in case the load falls. Okay, very good. This one is okay. If let's say you don't know what safety to write, if it's an electric one, especially if you're using large current, you turn off the circuit when you don't use to prevent overheating and wear gloves. If there's something that can fall, use safety goggles or safety screen to prevent the elastic cord from sudden. Imagine if, let's say, for no reason, the cord breaks. So it's like a rubber band, or it will fly, it will fling into some random direction. And one of that random direction is your beautiful face. Okay, so use goggle lah. Okay, or do the experiment inside behind a safety screen. Oh, this one cushion sandbox. Just think about your paper 3. Okay, so this one got another D mark. Let's calculate how many marks this person got. Oh wait, we need to evaluate the diagram. Okay, so Miss Ellie and I are very different people. She will draw the diagram first. I draw diagram last one. I do everything first. Then I think, okay, I tell all the story now how to draw picture. Because I'm not a very picture person, if it's not pretty obvious by now. All right, so what needs to be on the diagram are these things. Okay, let me show you. And as usual, you can always refer to the mark scheme. So this is a pretty good example. Label, elastic cord. Label. Okay, so my friends, everything that is important has to be labeled. So if I don't see elastic cord label, is an automatic 0 already because you didn't label. Label this one. So how do you know you must label these things? Look, the whole experiment is about the elastic cord. If you never label the elastic cord, then how? So this one need to be labeled. So the mark is gone already. Label pulley. Pulley also didn't label. Haiya. Okay, got load. Other end passes over a pulley. Okay, this one got, but you never label the pulley. Okay, but I want to comment the retort stand. But also, is this a retort stand? Oh no. Okay, let me see if I can find a nicer drawing or a different drawing. I think there are some sample answers that you can look at in your OneNote. The loading is slow, so slow. Okay. So the diagram should look something like this. The generator, you connect to the vibrator. Maybe you put make sure you, so normally, right, if I'm drawing this, I will also include a G clamp here one, because I know we clamp the pulley. But in this case, they never insist lah. If you've ever seen a pulley in a lab before, again, at this time, Google is your best friend. The pulleys tend to look like this. You know. So we need a clamp thing. It's the pulley. We tie the string, then we loop around okay. Of course, you can turn the G clamp around and have this slightly higher so that there's more space for the string to vibrate. Meaning you will clamp it like that. Okay. Then there's more space for the string to vibrate. Pass the spring over like this. Cool. Okay. So something like this lah. Use ruler and draw, and please label the important characters. If you don't label the important characters, then it's no good. Okay. So there is a question asking us, when do we need to include the line pass through the origin or don't pass through the origin? That is pretty easy to tell what we need to do. And let me go back to the, oh no, wait. Let me go back to the question. Okay, so if you look back at your data analysis, this one, this one, this one, do you have y-intercept? Look at the equation. Y equal to mx. Got plus c or not? Is there a plus c here? So y-intercept is 0. So passes origin. All this working is going on in your head or in page 1. It will not be marked. Okay? That right? But it's okay lah. So no y-intercept. So must mention pass through the origin. If got y-intercept, then must mention straight line with y-intercept or straight line that does not pass the origin. Yeah, this one is very important to them. And of course, important to the experiment too. Okay, let's total up this person's mark. Okay, so the method mark is 2 out of 4. So now the highest possible score this person can get is 13 already. 2 out of 4. Analysis is 3 out of 3. How many extra detail? 1, 2, 3, 4, 5, 6, 7, 8. Got 8 out of the maximum possible marks you can score is 6, I think. Yes. So maximum is 6 lah. You get 8 out of 6 means it becomes 6 out of 6. So the total mark here is 13 out of 15. Pretty good. Okay. So if you miss out things like, for example, you're not used to labeling diagrams, right? I'm also kind of like, how do you probably need to clamp this to a rod one. I expect some clamping action happening here. If not, then it feels like it is floating. I can give you a benefit of a doubt and say this is a retort stand, but I will definitely prefer if you mention that this is a clamp and this is a clamp, because obviously the string and the vibrator, this is not a bad setup because you can actually observe, you give more space for the string to oscillate. Okay, so there is before I move on to question 2, any question regarding question 1 you can send to the chat now. I want to talk about what is a signal generator and what is a CRO. Okay, because I think, I'm so sorry, you may not have seen it before. Okay, so if you want to think about generator and CRO, sometimes they are even the same device. Yeah, I want to find one that looks a bit more normal. Actually, they all look the same. It's a box. It's just a box. You can call it also a function generator, because it can generate its own function. So a signal generator look like this. And a signal generator be a CRO? Are they the same thing? Are they a different thing? It can be both. But they have different function. It's just like your multimeter. Can it measure resistor? Can it measure, try to find a nicer diagram. Can it measure current? Can it measure potential difference? Can. Also can. But mainly for measuring purposes. So this is a CRO. Partial one, but I like it because I can see the wave, just like I can see the wave here. So what is going on? It can be a 2-in-1. It really depends on the design. This is the older school version, the one that I use in labs. So you can see there's a time base here. You see all these small intervals. So what we would suggest is this one is mainly for taking readings. Okay, signal generator is used to generate signals. Okay, so when we say alternating current frequency, peak values, etc., this CRO is to read period or frequency, which is what we did just now. So a better format of the drawing would probably means to include, can it be a 2-in-1? Can, but you want to treat things like, super old school Miss Lee in school time one, then there are actually 2 devices lah. Okay, you also have a CRO. So CRO here is for you to read. This one is to read period, and then from period to find frequency. Okay, this signal generator is to send output voltage to vibrator to cause vibration. Of course, this output is alternating current. So it also generate alternating current. So you can see it as more as one as an output and one as an input. Signal generator is output. Whether the output is sending the output voltage into the vibrator so the vibrator will vibrate, or generating alternating current for you. So if you see here, I can adjust, I a bit off lah, but frequency, amplitude, all this I can adjust, or I can press button, and then create different pulses, right? For this one is mainly for measurement. So I can connect this one directly as an input to measure things. So this one is to receive a signal for measurement. So what I can do is, because I'm connecting it to the same vibrator, this one here, they say 50 hertz, I can double check and it looks like 50 hertz. Oh. But in the signal generator itself, you can press unless you have trust issues. You can press your own frequency here. So actually you have signal generator, you don't really need to read. So let me introduce to you the mark scheme now. Because you may be like, why if I don't write the CRO? Can I still get a lot of marks? I mean, you will lose a lot of D marks. It's not really a problem. Okay. So keep L constant, use chord of the same material, use CRO to determine frequency or period, how to find period from CRO, how to find frequency from period. Okay. Repeat the measurement of diameter along the coil average. This two is standard one. You only need 6. Measure mass of the load on the top pan balance. Okay. Details on determining the frequency at maximum amplitude, i.e. increase frequency until amplitude starts to decrease and then decrease frequency. Increase frequency, oh yeah. So basically you increase the frequency until the amplitude is maximum. How do you know this one is maximum? It's when you go forward a bit, it begins to decrease again. So this sentence, in case you are wondering what this sentence means, write this. But what this means is, let's say you put 10 hertz, then the string look like this. I don't know what number lah. Yeah, 10 a bit small. 50 hertz. Okay, then you get like this. And then 60 hertz, you get like this. This pattern you see, okay? And then 70 hertz, you get back this one. So you know the harmonic or the standing wave is between here to here. Because the amplitude, if you do past year question, amplitude of stationary wave, okay, against frequency will increase, decrease. Then here is actually your resonance. Okay, so somewhere here to here lah. That's what they mean by increase the frequency until amplitude begin to decrease and then decrease back again. So increase until decrease and then decrease again to find somewhere here where the amplitude is the biggest. May not right. It may not happen. Who knows? Okay. So again, the safety goggles. So if you talk about 1, 2, 3, the first 3 mark definitely will get right. Okay. 4, 5, 6 is good enough already. You don't use a CRO, you can still score full marks. Okay. This one is very standard. Try not to use log and lon. It will give everyone a headache, including your person who is marking. Okay. Because then your K will be equal to M over 10 to the power of 2 times Y-intercept. Why you do this? Why? Okay, anyway, never mind. Vibrator connected to signal generator. You don't need a CRO, but you definitely need a signal generator because how else would a vibrator vibrate? You need to connect it to a power supply. The power supply here is the signal generator. It generates or creates alternating current. So increase or decrease the frequency until stationary wave pattern is observed, which is what the candidate wrote just now. All right. Measure a diameter of coil. So this one is the very standard one that most people will get. It's all this extra detail that if you don't use a CRO, then you will lose 1, 2, 3 marks. And then this one is just a bit of you only know how to write this if you actually do the experiment. Can we connect CRO? We are connecting it to a vibrator. The vibrator has a motor. Let me see if I can find. Let me see if I can find. Okay. This is short enough. I got this from the Institute of Physics video. Let's share sound. I think he will play some music. Share sound. Okay, like.
Thing, a signal generator. It's an incredibly useful device for teaching about waves and sound. It's essentially an AC power supply, which, as well as letting me change the voltage or amplitude of the output, also lets me change the frequency. And I can demonstrate that very simply using a loudspeaker. Now, if you are going to connect a loudspeaker to a signal generator, you need to connect it to the low resistance output. And on this model, that's conveniently labelled low. I've got the frequency set to 4 times 100, so 400 hertz, and I've got the amplitude set to 0. This is what happens when I increase the amplitude. You can clearly hear that as I increase the amplitude of the output, the sound gets louder. And when I decrease the amplitude, the sound gets quieter. And this is what happens when I change the frequency. What you should have heard is that as I increase the frequency of the output, the pitch of the note gets higher, and when I decrease the frequency, the pitch gets lower. In fact, this is a really simple way to demonstrate how the properties of sound depend on amplitude and frequency. Another way of looking at the output from a signal generator is to use an oscilloscope. Now, when you're connecting an oscilloscope, you need to use the high resistance output. And again, that's clearly marked on this model. So let's see what happens when I change the amplitude.
I want to pause here and ask you to think about the question in the chat. Can we connect CRO and a signal generator to a motor? Currently, you see in this video right now, they are connecting a CRO and a signal generator to a speaker, right? Isn't speakers kind of like a motor? It vibrates the diaphragm. That's why you hear sound.
Again, you can see that as I increase the amplitude of the trace on the oscilloscope increases. And when I decrease the amplitude of the trace also decreases. Let's take a quick look at frequency. Now, it should be clear that as I increase the frequency of the output of my signal generator, that increases the frequency of the trace on the oscilloscope. And obviously, when I decrease the frequency of the output, the frequency of the trace also decreases. Now, this is a really lovely setup for investigating the properties of sound, and you can do lots of other interesting things with it. One of the things I like to do is use it to test the range of frequencies my students can hear. It's a really simple experiment. You connect the speaker, you set the frequency to about 10,000 hertz, which most of your students can hear, and you ask them to raise their hands. You then gradually increase the frequency and tell your students to put their hands down when they can no longer hear the note. You then do the opposite, decreasing the frequency, and tell them to put their hands down when they can't hear the low notes. And that way you can determine the range of frequencies your students can hear. There's another thing you can do with a signal generator, and that's to change the shape of the waveform. So far, I've been using a sine wave, which gives a nice clear note, but I can also have a triangular wave, which sounds a bit like this, and a square wave, which sounds like this. And that sounds absolutely awful until you turn it off.
Hey, so can we connect a CRO and a signal generator together? Nah, this is what he's doing, lor. Okay, let me see if I can zoom. No, I cannot zoom in on the video. I guess I will just have to crop this whole thing. Okay, lah. This is the best I can do for you, besides doing the lab with you. Okay, nah, lie. Okay, see ya. This wire, this white wire is connected to the microphone. No, speaker directly. What am I talking about? Okay. The CRO is connected directly into the signal generator. So the signal generator is feeding two output concurrently. One of the output is into the CRO. Look at the wire. I mean, his hand is covered lah, but you see the red wire connect here, the black wire connect here. Okay. And if you check out the wire of the speaker, you see this white color one. I know a bit hard to tell. Let me see if we can see using the recorded version. I'm not sure whether you can see, but here what is happening is it's actually a wire pair. Remember your communication chapter, you have your wire pair. So this wire pair, one of the wire is going to the positive, one of the wire is going to the negative. So the thing about the signal generator and the CRO is there's no such thing as one input can only go to one place. One output can only go to one place. One output can go to many places. Parallel connection, correct? Just like one battery, you can connect to several resistors in parallel. So this signal generator is connected in parallel to the CRO. The CRO will detect the waveform. It's also connected in parallel to the loudspeaker. The loudspeaker will play the sound that you can hear. Okay? So yes, we can connect the CRO to the signal generator. It doesn't really matter how you draw lah. Same wire. You can draw to the signal generator also can. Okay, and as he mentioned just now, every CRO or every signal generator that you encounter in your lab, they all look different. Please read the instruction manual that hopefully is provided to you before you step here, step there, and then you fry a resistor inside, and then we need to repair it, and it's going to be quite expensive. Otherwise, it's okay. All right, so any other questions regarding signal generator and CRO? I think I shall include this nice photo here. And connect together one. Let me know if you're okay. And I can move on to question 2. The CRO. This is your signal generator. I mean, I played a lot with these kind of things in university, but for demonstration purposes, I am sorry that you weren't given a chance to watch this in person. Yes. For signal generator, can use instead of power supply? Can, but we only use signal generator as a power supply for alternating current. We use signal generator as a power supply for alternating current, not for DC, because it's too inefficient. Where did I don't remember where I labeled it, because it's too inefficient. Did I put it here? No, I didn't. It's too inefficient to look for DC. I can use a battery. So signal generator is output, but it can be output for AC. And the output AC can connect to a motor. So this thing can be a speaker, it can be a motor, it depends on what you want. But generally for a signal generator, the output device here, okay, is to send V out to vibrate or generate alternating current. And then the CRO is normally to read period or amplitude lah. If let's say I don't know for what reason you want to read the amplitude. Okay, so for equivalent experiment of using the signal generator, I would suggest you look at this question in your P5B, set 7. Okay, and as you can see, the entire examiner comment is here, the CRO is here. So you can talk about, in this case, there is no diagram at all. So you actually need to think about, let's say, for example, you see this one. The student is investigating how the peak alternating current I0 changes with frequency in the circuit containing a coil of a wire. Okay, so we know it is suggested that this relationship is this. So how do you measure peak alternating current? You will use the CRO to measure. How else do you know what is peak? This is not root mean square. Okay, and then how do you change the frequency? Signal generator. Okay, So after that, again, you list down all your things. So a signal generator is alternating current signal generator. You connect your CRO here. The difference between this and the standing wave thing is instead of having a coil here, because this is I0 through a coil of wire, is that we replace this coil with a motor. So if you are talking about this drawing, hang on. If you're talking about this drawing for this one, what we are doing to the CRO is we are connecting it this way, but instead of having some coil here, we don't have the coil. We have the coil out here. We connect this to a motor, the motor of the vibrator, like that. That's all. The setup is the same, and we don't need the ammeter because we're not measuring current in this experiment. Okay, but for this one, okay, you think about how you want to determine the relationship between I0 and F, and then find L. So again, when we linearize, Y is equal to mx plus c. Okay, what I will do, again, this is, you have to go and try the experiment now. If not, I will have to go through the whole process again, and it will take some time. But just so you know, if you check the mark scheme, okay, the variable frequency AC supply or signal generator. Dude, a signal generator is a variable frequency AC power supply. Signal generator is variable frequency AC power supply. MCKL is Methodist College Kuala Lumpur. Same thing. Okay. How to measure V across the power supply or current across the power supply? Use a CRO. Okay. Measure current using an ammeter. So you will talk about all of this. So go and study. I think if you cover all of this, you are okay. You are quite ready already. If there are certain experiments you never see before, you don't have time to read, refer to the sample. Okay. Can you you just draw a box. Just label this signal generator. It's okay, both is fine. What cannot happen is if you don't label. So just label alternating current signal generator. Just label. Okay. So it's the labeling that matters for paper file diagram. Okay, you can draw a box, you can label signal generator, you can draw the AC symbol because we are dealing with alternating current in the coil. Okay, so there's another question about May, June 17 paper file 2. So let's look at the question. May, June 17 paper file 2. Oh no. Can we use the CRO for May, June 17 paper file 2? Okay, this one. What is our variable? Investigating the motion of a small cube on the turntable. Okay, sure. And you want to test the relationship between F and R. Okay, and your question is, so basically I will turn the turntable faster and faster, faster and faster. And maximum frequency for which the cube does not move. So I turn faster and faster until the cube begin to slide. Then I take down the maximum frequency. And then I repeat the process again by putting the cube at different value of R. So maybe I put the cube here, and then I increase the frequency until the cube fly. Repeat again, put the cube here, increase the frequency until the cube fly, etc., etc. Okay, so what to do? Power supply connected to motor. Okay, you don't need to, do you need to measure the frequency of rotation? How do you measure the frequency of rotation? To change the frequency. So this is how to change. But how do you measure the period of frequency of rotation? It doesn't have to be a CRO connected to the power supply. So it can be, I legit take a stopwatch and time. I can see the turntable turning. Okay, what you cannot see in the previous two experiments is current changing direction. Obviously, no one can see that unless you have superpower, or string. Remember the string was oscillating so fast in the GIF that I show you. So that one you cannot see. Whatever frequency that you cannot observe, you will use a CRO. In this case, I guess they accept stopwatch and light gate attached to a timer or a stroboscope because it's a kinematics one, you can see. Okay. Can I use a CRO for this one? I guess it's subjected to the marker. Rotates in one direction and not. CRO supposed to be able to measure both current and voltage. Supposed to lah. Okay. The answer to whether I can use a CRO for this is I don't know. Because the power supply, if you want to be able to measure during using a CRO, this power supply have to be alternating current, and they didn't mention that the power supply have to be alternating current. You can have a direct current motor one. So there is no like any compulsion for this to be an alternating power supply. So you don't really need a CRO. Okay. But how do we draw a workable circuit for this one? First, the mark scheme is not very helpful one. Circuit must be workable. I draw lah, since you asked. I draw. Let's steal this because why not? Which one was I using this? Okay, yes, I was doing this. Okay, so if let's say I want to draw a workable circuit diagram for this, my turntable will be connected to a motor. So if you feel a bit insecure, you can always draw a front view, a side view. So this is your turntable. And below that, there is maybe some motor here. You label motor. And then this one must be connected to a power supply. So generally, I would reserve signal generator and alternating AC power supply. This one, this setup, I generally reserve for waves or alternating current. Kinematic things, I generally don't expect that to happen because if it's kinematics I can see, then light gate will make more sense. Okay, so the answer to that is I don't know. If it's not in the mark scheme, it is unclear whether you will get marks or not. Okay, so we connect this to a power supply. And then on my turntable, if I want to use a light gate, I'm going to put a marker here. So I label. This is my marker. Okay, you can connect two wires to the power supply. What else do you need? Let's see. Wait, where's my question? Power supply connected to a motor, two LEDs within turntable, circuit must be workable. What do we need to keep constant? Change R, keep M. Safety screen, 10 rotation. Use a balance to measure the tube. Ensure the surface is horizontal. Use ruler to measure R. Ensure R is measured from the center. Nothing much really. Just like that. This is a workable circuit. Where are you going to put your light gate? Fine. I draw a table. Give me a sec. I can hear my teacher scold me. Where is your table? Why are all your instruments floating everywhere? Fine. Must have two LED lah, got input, got output lah. So this one is your power supply. This one I just simply draw. Okay, you can draw better. Okay, where to put your light gate? I will place the light gate here. Okay. So this is light gate. And then I must make sure I clamp the light gate lah, because the light gate is not going to just stand there on its own, right? Okay, so I will clamp the light gate label. Okay, hang on. Let me reposition my light gate and my marker and clamp it. So I will always label the clamp because I don't always draw the nicest retort stand. Okay, and then this is the light gate. So whenever it detects the marker passing through, it will count the time taken as 1 period. In this case, if the light gate is connected to the data logger, just to be safe, always take more period. You also, when you turn on the power supply, right, and the turntable start to turn, it's not going to turn to maximum speed immediately, correct? You imagine you do this, imagine you turn on your fan now, you turn on your fan at home, you press on, immediately your fan go to full speed, it's going to take a few seconds to accelerate, which is this point, where they say, this part here, wait for the turntable to rotate steadily before increasing frequency. Okay, so if I want to increase frequency, you see here, change frequency by adjusting the variable. So you either mention inside your methods or your steps that you have a variable power supply, and you will change the power supply. Let me show you how a variable power supply looks like. And if you're going to like tell me, Miss, is it a box again? Yes. I don't know what you were expecting, but it's a box again. Look, physics people are very like, we're going to use back the same thing now because it's just going to use the same attachment. Anyway, and we get to charge people 4,000 for this. So one school buy 20. This is probably why MCKL don't have now. MCKL only got one. So you can see here, this is my variable power supply. Ooh, I can zoom in. Look at all the beautiful switches. So pretty. Okay, let's see. This one looks like direct current. This is the ground. This is also direct current. Miss, what is a slave and what is a master? I don't want to tell you. Go find out. Go Google. Master and slave in circuit. There's a wave display. Actually, it's the more expensive one now. I see the okay, no, never mind. A bit lazy though. But this is how it looks like now, okay? So it's a variable power supply that I can also adjust the power supply. Miss, is this also a signal generator? If I can't change the frequency, then it's not a signal generator. Looks like I can only change the output voltage. See, there's no frequency here. Okay, looks like it lah. Every box is different lah. It's like every phone is different. Okay, so you either change the output voltage of the power supply or you connect a resistor here. I really should draw this better, but you can connect this one to a variable resistor R like this. So you change the variable resistor, you change the current into the motor, you change the frequency. Okay. But I still think that it's better to change the power directly inside this one. So basically this motor, right, it will respond to the power supply, which is what this point is trying to say lah. Okay, change the frequency. So you should mention that the frequency of the turntable is changed by changing the output. Okay, and then we increase the frequency until the cube begin to move. Okay. Time at least 10 rotation of a turntable. So use a light gate lah. If you want to know what's a stroboscope again, Google is your friend. Go and find out. Stroboscope is a bit old school lah. This one, light gate, is a bit more legit. Okay, 10 rotations of a turntable. So whenever you have any kind of repetitive motion, whether it's oscillation or circular motion, please repeat 10 times, even if you have a data logger, to decrease the percentage error or the percentage uncertainty. Okay, so did I label everything? Oh, no, this diagram will not get marked. because why? I miss out my mass. Cube, my cube is here. Okay, can now. I think I'm satisfied. Okay. You want to draw top view also can. You just need to, I don't know, draw a dotted line like that. This is motor. Dotted line means it's below and you cannot see. Label motor. Then you connect out to two LED. But I always find drawing dotted line a bit uncomfortable as a student because I don't really know whether, I mean, CIE, I was told when I go for courses that they are not very strict. Then it means as long as they understand your drawing, you are okay lah. Variable power supply. Just make sure you label everything. And I think here I should also label R. All the important characters must, this one is like poster for your story. So all the important characters must appear in the poster. Okay? Don't just put Iron Man, must put Captain America and Black Widow and all the other people. So same thing lah. We are measuring the distance between R of the metal. Oh, holy cow. Wait, label R only. Between the metal cube distance from the center. R is here, my bad. Turntable, okay? And then how to change the frequency I have drawn here. And how to measure the frequency I have drawn here. This part here is to measure F. This part here is to change F. You see, whenever you want to measure something, everything about it has marks. So this is another alternative drawing you can draw. But I don't know how you're going to draw the light gate. You're going to draw the light gate. So I guess can. You can also draw top view. I prefer to draw side view. Easier for me to put my things because I'm imagining I'm looking at it from the side of the table, which is easier for my brain to brain, if that makes sense. Okay, wow, we covered 2 questions today, very different ones. Thanks for the chat. Other things to note is that the spirit level to check that the turntable is horizontal, clean the cube and the surface, use a rule to measure R. Method to ensure R is measured to the center of the cube. You put a marker on the cube or align the front and the back of the cube by a set distance. Okay. Method to determine the center of the turntable. Measure 2 diameters and then you draw lines and then you find the intersection. You know what I mean, right? You measure 2 diameters. Then you draw one line here. Wait, change color. Draw one line here. Draw one line here. Wherever the intersection is, there'll be the center. Okay. These are all extra detail. You don't need to write all. You just need to write 6. Use a safety screen because the cube can fly if you change the frequency too quickly and it may hit you in the face. Goggles is not good enough because goggle can't cover your beautiful nose because they want to hit you in the nose. Okay, so anything regarding frequency is D2 and D3. 10 rotation, frequency is 1 over period. Okay, because your data logger will measure the time taken for 10 cycles. Repeat experiment for each R and average F. CI is very specific one for each independent variable and measure dependent variable. We need the mass of the cube, so use a balance to measure the mass of the cube. Okay, spirit level to check that is balanced. I think this one is okay. And the rest is pretty standard. Analysis, I hope you are fine. If you are not fine, please go do more questions. There are tutorial videos about how to linearize graphs in wherever you normally watch your lectures. Okay, time to go to the last question. Question 2. We normally spend a lot of time in question 1. Why? Okay, time to drop a ball in a liquid. We are still doing, which year is this again? May, June 20. Yes, May, June 20. So I don't know. People who just joined, hello. So this May, June 20, paper 5.2. I think this is also in your homework somewhere. So we have a ball. It's falling through liquid. Okay, we have seen this before so many times in our AS. Okay, so the student determines the speed of the ball between P and Q and measures the thermodynamic temperature. So fancy. Temperature in Kelvin lah. Okay, viscosity is a term used to describe the viscous or the drag force acting in a liquid. Viscosity has a unit of Pascal second. Okay, the viscosity of the liquid is calculated from the speed of the ball. Experiment is repeated for the same liquid at different temperatures. It is suggested that viscosity, nu, the pronunciation for this symbol is nu, okay? And T is related by the equation, this one. A graph is plotted ln nu on the y-axis and 1 over T on the x-axis. Determine gradient and y-intercept. This is, you either get or you don't get the marks, that's all. So this one, to linearize, we will ln both sides, okay? My friends, if you don't know the ln identity, because maybe you don't do maths, but you're very brave to do physics, this is generally what we do lah. We add ln to both sides. Exponent, then we do ln. 10 to the power, then we do log. Okay, so here will become ln nu. Wow, so danger. For after a while, I will start writing ln square already. So this is ln. So this ln, okay, what will happen is this h and this e, I'm going to separate. Okay, so what I'll have is I'll have ln e to the power of e over kt plus ln h. So I'm doing ln AB is ln A plus ln B. This one is A. This one is B. Okay, and then I can bring things down. Ln nu is equal to ln E is 1. So what is left is E over KT, because I can bring this power and put in front. Okay, times ln E. But this one is 1, okay, plus ln H. Again, compare with your good best friend equation, y equal to mx. But what is m? 1 over t. So this one maybe need to rearrange a bit. 1 over m, can? So y is equal to mx plus c. So this is x, this is plus c. So this one is your y-intercept, and this one is your gradient. It's a do or die KPI. Okay, so this is no problem. Do as many steps as you want or as little step as you need. This is the answer. You don't get, then no marks lor. That's all. Okay, so moving on. Let me pull this aside first. Okay, next part. Table. Okay, you see this 10 to the power of -4. You see this 10 to the power of -4. So wherever you press here, you should press ln 12.3. The 10 to the power -4 go into the, so you just take this one kind of already. Okay, so the second thing is this one, 1, 2, 3, 3 SF. So when you move here, it should be 3 or 4 dp, this one. So 2.510, 228, 213, 192, 172, or mark scheme all agree. This is good. So basically, the candidate, what plus 1 SF for everybody. Okay, can. So 1 mark here. Absolute uncertainty, go from 0.02 to 0.04. Okay, correct, 1 mark. So I'm not sure which identity he used. The options are, you can either, to get this number, first option, you can take identity, which is del x, or rather del nu over nu, because uncertainty in ln x is equal to del x over x. But uncertainty in log x, uncertainty in log x is equal to 1 over ln 10 times del x over x. So this one is this type. Okay, or you can take ln max minus min. What's the maximum here? Let's see. 12.5 minus ln, what's the minimum here? 12.1 divided by 2. You like lah. It doesn't matter. As long as you go from 0.02 to 0.04, you're okay. No problem. Okay, plot a graph, include error bars, draw a straight line, and worst best fit line. So there are 4 marks here when I stare at the graph. Okay, the first thing I look at is the plots. Did we plot? Okay, I'm going to outline the plot so that everyone here can see better, including me. Did we plot at the corner? Plot at the corner? Yes. So the examiner will check like this one. And because your paper is scanned, they can zoom in like what I'm doing now to check. And if you're an examiner checking like 200 script, your patience will be quite thin lah. So please make the work of your examiner easier. Okay, so 1, 2, 3, 4, 5, 6. We shall assume our friend here plot correctly. And our error bars are also looking good. So when you draw using pencil, hopefully a thinner pencil, you will draw something like this, and then down, and then like this. So for this one, it's plus minus 0.04. No, wait, 0.0, yeah, 0.04. 2424. Okay. This is 1.57, right? So here is 1.57 plus 0.04 minus 0.04. We should know where you start and where you end. I do not recommend using arrow. Please use lines like this. Okay, so I assume plot correct. Error bar okay. All right, if I'm actually marking, I will check more thoroughly lah, but it looks fine. 4, 4, 3, 2, 2, 2. Good. Okay, let's check the best fit line. So they always give you a bracket or a range. You wouldn't know whether you fit the range or not until the mark scheme come out, because I don't write the mark scheme. But in this particular experiment, the range is from 1.65. Where is 1.65? 1.65 is here. 2.93 to 2.96. So 9192, 2.93 is here. Oh, see, I think our friend got draw here. 2.93 all the way to 2.96. So the best fit line has passed through this bracket. Okay. The other upper end bracket is we should pass through 2.45. Okay, here to here. Okay, so my advice to you if you struggle with drawing best fit line is go and watch the FM21 video where Miss Ellie and I show a simulation and explain best fit line and practice. Go practice. Practice by doing some past here. You have to practice one. You see, I got skill also no use ma. It's like you see people making dalgona coffee. Wow, so fluffy. Wow, so nice. You go and make everything fall apart because you never practice. Okay, anyway, this one looks okay. The error bar, the worst fit line must pass through all the error bar. I hope this candidate got label, or if no label, then that would be very sad. Oh no, there's no label. No label. Haiya. No label will be an auto 0 liao. I feel rip. Sorry, I'm so sorry. 2 out of 2, plot correctly, 0 out of 2. No label. Haiya. No label, very pain there. And where is my triangle? Is there a triangle here that I can't see? Wow, no triangle. I think maybe this candidate want to give my life easy. So no triangle. Dot, 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 dot. So imagine this is your best fit line. I cannot see a triangle. I cannot check coordinate. I cannot check coordinate. I got nothing to check already. So this one is 0. Let's assume correct. Okay. And then I don't know what to check because I cannot check read off. Okay. So you see, if you take data points, I would prefer if you draw a triangle. If not, I cannot check your read off. I don't know which point you take. Triangle only. Okay. Clear substitution of triangle. Use triangle. Draw a big triangle. Okay. Next, if I see this method is correct, okay, can lah. Get 1 out of 2. Let's see if I can guess which one is the best fit line. This is the best fit line. You label something like this. Okay, you know what? I pretend I'm the candidate. I label with pencil. Okay, so when lines are close together, you should label at the end. So this one is best fit line, and this one is worst fit line, something like this. Make sure your worst fit line passes through all the error bar. This one, no problem. Basically, you're trying to draw the maximum or the minimum gradient line. Okay, so I don't suggest using data points without context. So please try to also include the triangle. Please, where's my triangle? Okay, for the first one, does the absolute uncertainty must be 2? No. 1 SF is perfectly fine. Perfectly fine. You can be a bit like, what you can do is you can draw one triangle one. You just draw like that, lor. I think you can see the FatMarch 211. We show you 2 sample script. One person draw 2 triangle, one person draw 1 triangle. So 1 triangle will look something like this lah. I don't want to do this here because I need to scroll and it's a pain. So I'll do it here. So let's say this is your best fit line, your worst fit line. So what you could do is you could draw this triangle like that, lor. Triangle like that, lor. And then you can read this coordinate, read this coordinate, read this coordinate, read this coordinate. 1 triangle, settle everything. Can. I prefer drawing 2 triangles because I like to find corner plots lah. But you know what? It's okay. You can just read to the nearest corner. You're good. What's the maximum SF for absolute uncertainty? The maximum SF for absolute uncertainty, they didn't specify. So I personally think I'm comfortable with 1 or 2. The only thing that they say is allow a mixture of SF. So if there's anything that is more, if there's anything more vague than that, I have not met lah. So it's very vague. They say allow a mixture of what, 1 and 2, 2 and 3, 40 and 70. What is a mixture? Don't know. So I think I'm comfortable with 1 or 2. You may want to take 2 for this one, like someone in the chat pointed out, because, you know, the DP must be the same, okay? But this one is also okay. So it's fine. Anything more than 2 is a headache. In fact, 2 is already quite a headache because your error bar also must be corner plot. Okay, so if you watch the FM, so you know what? If you haven't tried the FatMarch 2.1 paper 5.2 yet, after this video, go take a shower, go and rest, come back, you do it, see if you can fit in exam time, and then go and watch the video. Because Miss Ellie and I got comment about number 1, 2 different candidates. I think you can tell which one is which one, because one I do, one she do, correct? So what kind of candidate will round off and what kind of candidate won't round off. And generally speaking, if you're short in time, round it off. It's okay. No problem. There's no mark difference, no outcome difference. I am substituting this because I want a triangle. And it's also unclear which point I mean, sure lah, you can argue, I take this point, I take this point. Can I just draw your triangle lah, okay? So that there's no argument. Can draw a triangle. And there's no maximum SF. Okay. Next one. Where are we now? Okay, so we found, do not include absolute uncertainty. Bless you, Christian. Okay, so we don't have to find absolute uncertainty. Very nice, very nice. So we just need to look for the Y-intercept. So student Student use y minus y1 is equal to mx minus x1. Such a further math student. Someone got the dot one. 1.80. So sometimes people ask me, can I put 1.80 here? Do I put 1.804 here? I suggest you take back the value from the front lah. But if you don't, also never mind. You just show your substitution clearly. Because when I see this, if I'm marking it, the first thing I'll do is I will check is the gradient correct or the gradient correct. Okay. Then I check the y-intercept. I need to find the point. Do I have this coordinate? Got lah. Okay. So I'm going to assume that you calculated correctly lah. Okay. So must use equation. We prefer y equal to mx plus c. Simply because it's easier to see for physics brain. Okay. Anyway, this one, gradient is e over k. So E is k times gradient. K is this one. Okay. You get this. Let me check mark scheme. Is there a range in the mark scheme? Okay, well, whatever range you put, it doesn't matter. There's no range. So the mark is actually here. And then this one is 2 or 3 SF. So this is the first mark. The second mark is H determined using y-intercept. Okay, Ken? So from here, you bring over lah. Y-intercept is ln H. Ln H is log base E, right? So E to the power of y-intercept is H. But then sometimes students ask me, why you got 10 negative 4 1? Because what is your y-intercept? Is there a negative 4 here? Correct? So when you think about ln y-intercept is ln H, this y-intercept, the 10 to the negative 4 is inside the bracket already. Let me change the pen thickness. Okay, this y-intercept is nu 10 to the power of negative 4 Pascal second. Right, whatever number you have here, your negative 3.67 is equal to ln H. So when you unln this, H is ln negative 3.67, you will times 10 to the negative 4. Okay, wait, unln, sorry, don't know what I'm doing. E to the power of this. Then you will times 10 to the power of negative 4. So in the beginning of the video, I have already explained why. If you unfrozen your ln, so this one is 10 to the power of negative 4 plus PAS, pass. Then this one, this H is also in the unit of 10 to the power of negative 4 PAS. That's why you can write them as equal what? Are we okay? Can? All right, so I assume our friend here, he pressed calculator correctly. So this one is okay with the negative 4. This is 1 mark. And the units, this one is in joule. This one is PAS, is 1 mark. Unit. Okay, so 3. Next, find the absolute uncertainty in E. Well, if you look at this calculation, to find E, you just look for the gradient. So you just need to find the percentage uncertainty of gradient. Okay, so percentage uncertainty of gradient, you scroll all the way back here. So when I mark, I will go back here and stare at this 0.08 divided by 1.80. Okay, 0.08 divided by 1.80, I'm satisfied. Multiply by the value of E. Value of E I can find here. I am confusion. Where? This one, shouldn't this be 2.48 times 10 to the power of negative 20? Oh, well, 0. What happened? What happened? And in actual exam, I will press the calculator. Okay, now I assume you press correctly. Okay. What happened? It is so sad because it's 1 mark only. Okay, determine nu for a temperature of 273 Kelvin. Okay, boss, time to rewind. It's rewind time. So we're going to rewind ourselves way back to the beginning, we have two options. Okay, option 1 is to use the linearized form of the equation. Option 2 is to use this equation itself. I will do both for the people. That's all. So this is one option. I can just start with this equation because this is the one that is given to me. Or I can use the equation of this straight line, slightly mangled, but still can use here. Okay, so bear with me as I transfer because keep scrolling. Okay, so first one. First one seems more straightforward, right? Got nu, I substitute everything. Okay, can. Before you start, you need to find H-E-K because I know T. T is 273. But miss, you see, we find E and H already. Okay, okay. What is K? There, this one. So we can do that. Nu is equal to, okay, what is H? H. 2.55 times 10 power negative 6. I hope the candidate pressed correctly. I didn't check the calculator. Negative 6. Confession time. Okay, exponent e to the power of, I'm going to take that answer here, okay? 2.48 times 10 power negative 20. The Boltzmann constant, 1.38 times 10 to the power of 23. Negative 23. Negative 23, sorry. Times the temperature, which is 273. So multiply 273. Okay, time to bring out my friend Casio, the calculator. Where's my E? My E is here. E to the power of fraction 2.48. You know what? For the benefit of people who don't have this calculator, I'm going to change the setup to normal line one. Just for you, okay? Where is my line? Okay, there we go. Okay, how to press this if you don't have this calculator? You just have the normal one, you know, the one without all the fancy smancy fraction things. Okay, never mind. You can still type the same thing, 2.48 exponent negative 20. Yours will look like this already. Then you divide by 1.38 negative 23. And then you divide by, is it 273? Yes, 273. Close bracket. Okay, you divide by these two things. Okay, now you press equal first lah. Okay, then you multiply by this times 2.55 e to the power of negative 6. Okay, 1.84 times 10 to the power of negative 3. Close enough lah. 1.84 times 10 to the power of negative 3. You see this one? 1.86 times 10 to the power of negative 3. Okay, I prefer like that. If you want to use the linearized form, can. You have to be a bit more careful. So you got ln nu is equal to gradient times whatever you substitute here, 1 over m. Okay. Ln E is 1 plus ln H. Okay, so temperature, wait. What is 1 over m? No, wait, it's 1 over T. What am I doing? Haiya, this one is T. 1 over T. Okay, so we are looking for ln nu, because we are looking for nu. We have the gradient 1.80 times, what was gradient? Where is my gradient? Times 10 to the power of 3. Okay, boss. Times 10 to the power of 3. 1 over 273 plus ln. Got H or not? Nah, we steal the H here. 2.55 times 10 to the power of negative 6. Okay. 2.55 times 10 to the power of negative 6. So we put everything inside. Then we press calculator again. But this one you have to be a bit more careful. Let me press my calculator first. 1.83 times 10 to the power of 3 divide by 273. 1.80. Okay. Plus ln h 2.55 e negative 6. Ding. I get this number. Negative 6.286. Don't forget, on your y-axis, this nu is in times 10 to the power negative 4 PAS. So you have to bring over your nu will be equal to blah, blah, blah times 10 to the power negative 4. Whenever you unfreeze 0.286. Okay, press calculator again. Shift E. Negative 6.286. Okay. 1.82 times 10 to the power negative 3. Ooh, wait, 1.86 times 10 to the power negative 3. So is this needed? If yes, why? If no, why? So it's not the same left and right. So now here is where people get confused, no? Why sometimes need, why sometimes don't need one? Okay, here's a hint why you no longer need to do this. Oh, where's my pen? This is no longer needed. No longer needed. Why? Because this H is already in PAS. Go back. Where do you find your H? Here. Origin story. But this one is needed because you took something from the graph. Taken from graph. If you taken from graph, it means it is still in negative form. So this is negative 4, this is negative 4. You want it to not be negative 4, then you time already. So once we do it once, we don't have to do it again when we use back into the linearized format. Or you do 2 methods and you double check if you have time. But oftentimes I also want you to do question 1 with enough time. Okay, so this is better for the brain. Okay, just make sure everything you convert to the one without some weird hidden prefix inside a log or ln. So here we have already taken out the prefix for ln h, meaning this one instead is PAS, because this is PAS, this h is in PAS. Okay? This is nicer to the brain. That's okay, so just make sure you know what you're doing. So if this is already in, homogeneity, every term must have the same unit. So if I ln PAS here, then I ln PAS here, although these two technically is unitless, but the idea is the same. It is confined within the log. Or do this method. Okay, let's see how many marks we got. Okay, so I understand this. Oh, I think this person took the Y-intercept directly. Also can now, whichever you do correct can now. 1 mark. So -1, -2, -3, -4. So it's 11 out of 15. So 11 and 13. So 11 plus 13. 13 plus 11 is 24 out of 30. No bad, no bad. I mean, of course, if he labeled the line, it'll be 26 out of 30, but it's okay. We all make mistakes. So just think about the whole paper. You need to finish it in 1 hour, 15 minutes. If you haven't done the FedMarch 2-1 paper, 5.2 paper, then it's a good opportunity for you to practice, or just try any variant that you haven't seen before that we haven't included. But if you have certain skills that need brushing up, whether it's log or lon, DP, SF, drawing best fit line, drawing error bar, or learning to actually frame the experiment properly such that you get as much marks as possible. Right? Look, the table one is just a technique. This person, or I don't know whether he got draw table or not, but go practice. If there's a skill that you don't know, paper 5 is all about skills.